Okay, so 10.8, we are looking at graphing polar equations. 10.7 is all about just the polar coordinate and understanding the grid that we're using, and now we're going to take a look at actually graphing this and comparing it with rectangular and so forth. So, in rectangular coordinates, there is some symmetry. We tend not to graph that way, though. Like sometimes we'll say, okay, a parabola is symmetrical with axis of symmetry, but it's rare that we graph one side and then we reflect it. From time to time we might, but more importantly, we interpret it and might use that information for application. With polars, you'll find that understanding where the reflection is can be really helpful because it can save a lot of time. When you graph a polar graph, you essentially trace around with a curve, and the direction that you go is really important, and it'll loop out a different type of picture. So understanding symmetry can be helpful. There's a quick trick to it, really, and if you use this idea about r of theta versus negative theta, that can be helpful. So if we think about cosine, for example, okay, and did I write this down in my own notes? If we think about cosine, and you think about cosine at theta versus at negative theta. So cosine of pi over 4, for example. Just thinking about the sign of it is really all we have to think about. Cosine of pi over 4, first quadrant, is positive, right? And if I said to you, well, what about cosine at negative pi over 4? Well, that's now in the fourth quadrant. Are we positive or are we negative? Positive. So right there's our reflection. We end up having, it's not the x-axis anymore, but it resembles the x-axis essentially. It's referred to as the polar axis. Okay? So it's reflective kind of up and down. It's a vertical reflection as the way we would typically look at it. Okay? Whereas sine, if I did that same thing with sine, you would get a negative result, right? Sine at pi over 4 compared with sine of negative pi over 4, the answers are opposite one another. So with sine, our reflection is then going to be about pi over 2. So that's what this first page kind of helps us out with. That's the quick check. Beyond that, I don't think it's super important to continue to do all of those things because you can just come up with a table of values and start plotting, and you'll pretty quickly start to find the pattern. And for me, I've always found that just plotting it by hand, it just helps me process it a little bit more anyway. We'll look at the very end how to graph it with a calculator also, because there are some more complicated ones that we would want. Max values, they're going to be relevant. They will depend upon theta, and then zeros occur when r is 0. So all those things that happen in the rectangular system continue to happen in the polar system. Here are some pretty funky, cool graphs, special polar graphs. Lemnicons, circles, and let me try to say that word the right way. Lemniscates, I'm not sure. And then the other one on the right are the rose curves. You'll see these referenced next year in BC if you take that class on. Not so much in the AB, but they're pretty neat. When they get more and more complicated, a graphing calculator would be more necessary and relevant. But in the calculus scheme of things, you'll be finding area of a petal, for example, perhaps volume, things like that of these different graphs. So at that stage, sometimes we are still graphing them by hand. Sometimes we are using our calculator to find that initial graph. But the main thing is understanding the domain. Like what part of the domain would give us that graph in the first quadrant only, for example. So I think starting by hand and coming up with your table of values is the best thing that we could be doing. Okay, so for our first example, sketch the graph of r equaling negative 4 sine theta. Okay. Negative 4 sine theta. Most commonly, we're just going to start with like a 0 to 2 pi mindset. And as we continue to go through it, we might end up changing that mindset. We might say, well, wait a minute, cosine versus sine, maybe it makes sense to go from negative pi over 2 to pi over 2 instead to get that reflection. Maybe it makes sense to go 0 to pi to see where the reflection is going to happen. We'll just start with 0 to 2 pi just to see where we're headed for the first example. Okay. Sometimes the table will be presented to you theta and theta comma r, sometimes r comma theta. Obviously, we're inputting in the thetas. So 0, pi over 6, pi over 3. Pi over 4s are commonly skipped and left out. Pi over 2, 2 pi over 3, 5 pi over 6, pi, 7 pi over 6, 3 pi over 2. Extend this a little bit. 11 pi over 6, and 2 pi. Okay, so let's see how this traces around and what kind of shape are we going to end up with. So we're inputting theta of 0 into that -4 sine theta, right? So sine at 0 gives us 0, so the r is 0. And we can plot that point. Let's plot one point at a time. So 0, comma 0, we're starting right there at the center. Then if I input pi over 6, well, sine at pi over 6, that's the y-coordinate, so that is a half. A half times -4 is going to give me -2. So at the angle of pi over 6, I would go to here first, but it's -2, so I walk backwards right there. Does that make sense? So again, for the angle of pi over 6, I start right here. Because the r is negative, I walked backwards from the center to that spot. Get rid of that line. Okay, so there's our second point. I won't curve it in, so we're done. Then pi over 3, so that's going to be a root 3 over 2 times a -4, so that's going to be a -2 root 3. So that's going to be in between 3 and 4. Again, the positive would be here. Because it's negative, we're coming down here. Please let me know if plotting these points is a challenge. Okay, I'll slow down and I'll go through it. Pi over 2 would be 1 times -4, we get -4. So again, pi over 2 is straight up. It's a -4, so we walk down instead to the circle of radius 4. 2 pi over 3, that would give us a root 3 over 2 again, so it's a -2 root 3. So we have that same point plotted right here. Five pi over 6, plugging that in, timesing it by -4, we get our -2.
Ms. Rodriguez, the R from theta equaling 2 pi over 3, it's -2 root 3, right?
Yes.
Okay.
Yes. Back at pi, sine at pi, 0, so we have 0. So we're right back where we started with. So I can complete that graph. What do we end up having in this one? It's just a circle. Yeah, and if we converted it, it would actually give us a circle formula. It's a circle of radius 2. Centered at 0, -2. So we're not going to convert it this time, but you could, right? That would be an xy coordinate for 0, -2. So once I've seen that, right, let's take a look at how the other points give us the same graph. So at 7 pi over 6, I'm going to get a +2. I'm just going to fill this in for us. At 3 pi over 2, I'm going to get a +4. 11 pi over 6 is a 2. 2 pi is a 0, right? So if I go to 7 pi over 6, I'm here. And I'm at a +2. So it would give us the same exact point thought about in a different version, right? If I went to 3 pi over 2, I'm going down, and then my r is 4. So I end up at the same point again. right? All of these obviously would map out the same exact way. 11 pi over 6. I'm going to end up right here in blue, in the 2 pi and the 0. So I didn't plot all of them, but every single one is just going to constantly repeat and repeat and repeat. So there would be no reason to continue to go there, right? So in this case, we could have just gone 0 to pi and would have seen everything because of how the symmetry is. All right, let's go for another one, complicated. So now we have r equals 3 plus 2 cosine theta. Okay, so to test our symmetry, each problem I'm going to build on like a new technique to get some more information from. So this one, let's actually test our symmetry. We're going to replace r comma theta with r comma negative theta. So what I mean by that, if you can do it with a single point, or you can do it more generally like we were doing before in the beginning of class. If I think about any theta that's positive and I plug it into my cosine, and then do that same exact theta that's negative and plug it into my cosine, I'll have the same result because the first quadrant and the fourth quadrant are the same. Cosine is the x value, so therefore the first and the fourth for x's are going to be positive. So therefore cosine of theta, this is the important part, is the same as cosine of negative theta. So because this is true, we are symmetrical about the polar axis. Which we would, in the rectangular world, we would refer to that, that's the x-axis, the horizontal one. Okay? So that means if we get some graph above this polar axis, we can just reflect it downward to complete the entire graph. So let's start with 0, right? Because if we have that symmetry, I don't need to plug in values on here. I need to do what's happening from 0 to pi. What's happening around there? So my angles that I'm looking at, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and pi. So if I evaluate r equals 3 plus 2 cos theta, that 3 changes things quite a bit. We're not going to end up with a circle anymore. Okay, so putting 0 in on cosine. Cosine at 0 is 1 times the 2 plus the 3, we get a 5. Putting in pi over 6, we get a root 3 over 2 times the 2, so we have a root 3 plus the 3. Let me plot both of those points, I'm sorry. So 0 and 5. 1, 2, 3, 4, 5. I'm right there for that one. And then what I do, just take that 3 plus root 3, for example, throw it in your calculator so you have a decimal version of it. I didn't jot it down, but it is in between 4 and 5. Okay, so I'm putting it right there on my graph. All right, now if I evaluate it at pi over 3, I get a half. Times a 2 is a 1, plus a 3 is a 4. So pi over 3, 1, 2, 3, 4. Good. Pi over 2 would be 0 plus the 3, so I get a 3. Two pi over 3, we get our half times the 2. I'm sorry, we get a negative half. Negative half times the 2 is negative 1. 3 plus negative 1 gives me a 2. Five pi over 6, negative root 3 over 2. So we get a 3 minus root 3 this time, which is in between 1 and 2. Right there. And then at pi, it's negative 1, so then it ends up 3 minus 2 or a 1. So I'm right there.
Is this a cardioid shape or cardioid or?
This is considered a limacon. So if you go back, when I reflect it, I'm going to do the reflection in red. You can do a rough sketch. I would do the point for point though. So I have this one, then I have this one, then I have this one, here, here, and here. Oh, cardioid's not wrong. I'm sorry. That is more specific. Dimpled limacon. Hold on. A over B is 1. In this case, it's a 3 over 2. So our B is smaller. Plus 2. Yeah, so it's a dimpled limacon, to be as specific as possible. Okay, so now let's do something similar. It's a 2 plus 4 sine theta. Okay, so I'm glad, I don't know who asked me about the cardioid, but this one is going to be a limacon with an inner loop because of the ratio of my A and my B. Right? So you don't need to know that, not for my purposes. But down the road, when you get into, if you get into BC and you take some of those kids, they take, even in BC class, it wasn't crucial that you were able to know their names. Just do it, okay? But anyways, r equals 2 plus 4 sine theta. So now if I do that quick test of sine theta versus sine negative theta, do I get the same result? And the answer there is no, right? Sine theta versus sine negative theta will equal the opposite answer, the opposite output, okay? Because of that, we will see symmetry over theta equaling pi over 2. So let's see what that looks like. Symmetry over, yep. So this theta being pi over 2 imitates, it's not, right? I'm not saying this, but it imitates our y equals axis, right? So now we're going to see the symmetry from the right side to the left side, which makes sense to us with sines because now sine, which is our y coordinate, is the same value in the first and the second quadrant of a rectangular system, okay? So now, that means that I do need to see some of my other values, right? If I only go from 0 to pi, I might not get everything, or I really don't have to do all of those. I could do like negative pi over 2s and things like that. So let's just, again, start and see what happens. So if I were to start with negative pi over 2, that's what I'm going to suggest. And then I'm going to go to negative pi over 3. And then I'm going to go to negative pi over 6. And a 0. And a pi over 6. And a pi over 3. And a pi over 2. Okay, that's what I'm going to suggest. And let's see where this takes us. So if I put in a negative pi over 2 to sine theta, sine at negative pi over 2 is negative 1. Right? Negative 1 times 4 is negative 4, plus 2 is a negative 2. Okay, let's see what that means for us. So negative pi over 2 is headed downward, right? That's where the angle is. And then my radius is also negative, what did I say, 2. So I'm actually going to go up to 2 there, right? So that point is here. Negative pi over 3. Okay, if I evaluate sine at negative pi over 3, I have a negative root 3 over 2 times a 4. So I have a negative 2 root 3 there. I have 2 minus 2 root 3. Sorry, I know these boxes are a little bit small, so I'm squeezing that in. That says 2 minus 2 root 3. In the calculator, I forget exactly what it was, but if I go, let me pull it from my graph. So negative pi over 3 is here. My r is negative, so I'm going to go the other direction. And that value should be between 1 and 2. It's right here. And now if I go negative pi over 6, well, sine at negative pi over 6 is negative 1/2 times a 4 is negative 2 plus a 2 is 0. Cool, so I'm just going to loop what I just did. Right, remember, everything is a curve with polar. There's no rigid lines, there's none of that. Then I can go to 0. Sine at 0, 0 plus 2. So look at that, I'm back at the same point. So that's where I actually can complete my loop, but I'm doing it in a little bit of a different order to get all of my points. If I go to pi over 6, sine at pi over 6 is a half. A half times a 4 is 2. 2 plus 2 is 4. I'm sorry, I didn't plot that last point the right way, did I? You guys should yell at me. R being 2, theta being 0 should have put me here. I was thinking pi over 2. Pi over 6, which is what we're on right now, and a 4 puts me here. There we are. Pi over 3 would give me a root 3 over 2 times a 4 would be a 2 root 3 plus a 2. So 2 plus 2 root 3. That is off our page. I'm going to estimate it here. And then the last angle I have here is pi over 2. 1 times 4 plus 2 will be the 6. So again, off of our page, up there a little bit more. And I'm there. So if I'm at the point of understanding symmetry, now I can take this whole thing and reflect it across what appears to be the y-axis, but it's really theta being pi over 2. So my reflection happens with that inner loop, as well as my outer loop. And it looks like that. Okay? And you can test any of those points, right? If you pick any of them, if you went with a pi or something like that, you would get the same value as the reflected side. So if I were to take one more step, like I kept saying I was going to do, I would be able to see that I have a maximum at pi over 2 comma 6. Right, once I have my table of values, I'm going to see the largest one, the largest r. And I have a 0 when theta equals negative pi over 6. And when we talk about the max r, it's going to be absolute value. So even if it came out as a -6, it would still be a maximum of 6. When you take this quiz for me on next Tuesday, everybody at home hear me too, this is going to be a file upload. You're going to give me work, pencil and paper, you're going to scan it in and submit it. That, or if you're sitting in front of me, you just hand it to me. That's also going to be fine. That way I'm seeing the process. I'm not worried about the formatting so much. I'm seeing the comprehension. I'm seeing, start to finish, table of values, graph, max, etc. Okay?
Can you explain again how you need the symmetry was pi over 2?
Yes, I can. I think about, let me stop the video. Okay, so when we're plotting r equaling 5 times 1 minus cos theta is going to be the same whether theta is positive or negative. So we are going to have symmetry with respect to the polar axis. So we're symmetry there. So that means we can plot theta between 0 and pi. That'll give us everything at the top half, and we can then bring it back down. Okay? 0, pi over 6, pi over 3, pi over 2, and then we're going to go to 2 pi over 3, 5 pi over 6, and pi. I have some decimal answers in here for this one, just because there was a 5 involved, and when you're trying to simplify root 3 over 2 and a 5, it doesn't do us much good. So if I put in my 0, cosine at 0 is 1, so 1 minus 1 gives me a 0 there, times a 5 is still a 0. So I start right there. Cosine at pi over 6 is my root 3 over 2. So I went to the calculator after that, 1 minus root 3 over 2, times that by 5, and I got 0.67. So I'm still pretty close to that first point. When I go to pi over 3, I have my 1/2. 1 minus 1/2 is 1/2 times 5 is 5/2, or 2.5. So now I'm at 1, 2 and a half. I'm right there. When I go to pi over 2, I have a 5. Because cosine is 0, so I'm just left with 5 minus 1, or 5 times 1. When I go to 2 pi over 3, so here's where it's going to start to grow because I'm 1 minus my cosine answer. So 2 pi over 3 is going to give me a negative a half. So I have 1 plus a half times the 5, and I get 7.5 now. So I'm off my grid. We'll approximate right there. And then if I go to if I go to 5 pi over 6, I get a negative root 3 over 2. So 1 plus root 3 over 2, then times the 5. That comes out to be about 9.3. So I'm even further out. And then when I test with pi, cos at pi is a negative 1. 1 plus a 1 is a 2, times a 5 is a 10. Put that out there. So if I continued with this symmetry across the polar axis, again, it's a little bit of a distorted shape because I don't really have this approximated to where I should. It should be more like circle-like on the left-hand side, less heart-shaped on the left-hand side. But on the right-hand side, it does look pretty accurate. This one, notice that the A and the B, in terms of our graphs, are the same, and that means it is considered a cardioid, the heart-shaped. So if I wanted to know what my max was, the absolute value of my R, the maximum, I would get 10 here. Right? And my zeros occur when theta was 0. And of course 2 pi, but we don't have to list that.
I thought theta was pi when. Oh, never mind.
Yeah, that's for the max.